All right, let's take a look at part C. For time greater than 300, what is the first time t that there are no people in line for the escalator? Okay. So, what do we know? Well, from part B, we saw that at time 300, the amount of people was 80. Okay. Let's see. There are 80 people left on the escalator. Now, keep in mind, all right, people are only getting on the escalator for the first 300 seconds. So this question is specific for t values greater than 300. So people are no longer getting on the escalator. All right. I would say, or to assume, however, that people are still exiting at 0.7 people per second. Okay. So we have 80 people left in line. How long is it going to take for those 80 people to get onto the escalator? It's just going to be 80 divided by 0.7. And if we do that, let's see, that's going to be an additional 114.286 seconds. All right, round to the nearest thousandth. Nothing about rounding here. All right, so we'll go with nearest thousandth. So that's how long it's going to take for these people to get out, these remaining 80 people to get out of line, okay? But be careful. The question asks for time greater than 300. What is the first time that no people are going to be in line? So after time 300, it's going to take that additional 114 and change seconds. So 300 plus is going to be 414.286 seconds. Okay, so just a little more than 414 seconds total for everybody to have been accounted for. All right, and that was just a 1-point problem. So a little bit of effort there to get that 1 point. If you didn't get it, not the end of the world. All right, moving on. Part D. On the interval 0-300, at what time t is the number of people in line a minimum? Okay, to the nearest whole number, find the number of people in line at this time. All right, so this is where, that integral that I have kind of in the bottom right corner can come in helpful. We want the amount of people to be a minimum. That integral will actually give us the amount of people at any time value. All right, so let's talk about the fact that we want the minimum. We're looking for the amount of people to be a min. Well, how do we find maxes and mins? Of course, we look at that thing's derivative. So we already know what the derivative of this is. That was the given overall rate of change, rate in minus the rate out. Okay, so there's the rate of change. What are we going to do? Well, we're going to set it equal to 0, right? And so we're looking for where r of t minus 0.7 equals 0, or where r of t equals 0.7. What I'll do is I'll just leave it like this, and now I'll use the calculator to find where these things intersect, okay? And in doing that, we're going to get t values of approximately 3.803 and 158.070. Okay, now just the window that I used that ended up being convenient here was x min 0, x max 300, because that's the time interval we're on. And then for y, I found that -5 to 5 worked pretty well for seeing this stuff. But again, things like that, you got to play around with it a little bit and, until you get a good view. All right. But those are the two t values. So, we're looking for the absolute minimum number of people here. Let's make a little table of values. So we're going to have time and the amount of people at that time. Okay. Now, look, don't neglect the endpoints in the interval. Sometimes they act as maxes and mins themselves, as we've seen in different examples in class before. So really, we've got these 4 values here that we're going to look at. Now, we already know the total amount of people at time 0 was 20, and the total amount of people at time 300 was 80. We already computed that stuff earlier. All right. What I can now do to calculate the total number of people at time whatever is use this. All right, so this is basically, I'm punching in 20 plus the integral from 0 to 3.803 of this thing. All right, which again was the R function minus 0.7. So you got to take a moment to be careful to punch that in. And then you're going to repeat with an upper bound of 158.070. Going through that process, okay, and I recommend that you take a moment to do it, to punch it in, to make sure you're getting these numbers. All right, and you should get about, let's see, excuse me. Whoops, I messed up. I gave you the Y values already. Son of a gun. Back it up. Back it up a little. Standard procedure here, folks. The times when they occur, the time values that I have where these things intersect, like we were talking about over here. Okay, the times, are 33.013 and 166.575. All right, so excuse me for that. These are the t values we're going to plug in as the bounds. And those are going to give us 3.803 and 158.070. Okay? All right, so sorry for the confusion. Hopefully you hung out. You hung in there till the end of the problem. All right, but now we can see that of all these critical points, the minimum occurs at this time value and is basically to the nearest number of people, 4. Okay, so let's see. The way they gave points was setting R of t minus 0.7 or a prime of t equal to 0, finding the times 33 and change, 166 and change, getting the answer of approximately 4 people. All right, and the work here acts as your justification. The table is your justification. Okay, so good problem, a lot going on, probably tough for the first one of these that we've kind of seen, but we'll see more and they'll get easier as we do. Okay, moving on to the next one.